Sundar Raman, Head Department of Mechanical Engineering, then Coordinator C. Manivel and Mr. Prakash. Sir, it is audible or not?
Sir, audible,
Yes,
sir.
sir.
Okay. Thank you, sir. Okay, sir. In my presentations, most of them are research scholars and professor. In my presentation, a few slides about the introduction, and most of the slides focusing on microstructure behavior of institute aluminum matrix composite. Then in this section, we can discuss more thing about the microstructure enhancement through in situ matrix composite. And what are the parameters we have to consider for that particular behavior of the material and particular changes we have to make to improve the mechanical property of aluminum matrix composite. The most of the cases, the material science, it is nothing but metal chemistry and physics enhanced with materials and processing engineering. This is the basic thing. Then when we come to alloys, it is a mixture of two or more elements to improve the property. Then mostly it is formed with the help of discrete element fusion to create new components. Most preference application of alloys to resist the corrosion and strength. Then when we look into the composite material, it is a combination of distinct material with superior properties. The major composite material structure improvement by matrix and reinforcement. The main advantages, it has superior physical and chemical property. Then the composite materials comes under the category of polymer matrix composite, ceramic and metal matrix composites. While we are considering polymer matrix composite, lots of applications are there. Mostly in medical field, we are looking new research materials in polymer composites. But the limitation is difficult to achieve continuous phase during the processing. It is very important, difficult while we are considering the polymer matrix composite. Then ceramic matrix composite. The main motive of this kind of composite to withstand high modulus, low shear strength, and it is very suitable for elevated temperature also. Most of the ceramic matrix composites are applying in high temperature applications in industries, but the limitation is brittleness due to the increasing toughness. While we are considering ceramic components, the temperature plays a major role. Metal matrix composite, reinforcement material dispersed in a metallic matrix. So we can consider the metal matrix composite through different preparation methods. Number one, powder metrology, the mixing of metallic powder, blending, compacting and sintering like that. The main disadvantage is the product size is very limited. It is not probably possible for a large size of component. Then casting, when we look in for casting, it is a very suitable method for a large size product. Then the casting, we are considering extrusive casting and in situ casting. Then we are looking to the metal matrix, aluminum metal matrix composite. It is a classification or subset of metal matrix composite. But due to the application of aluminum, a lot of research opportunity in aluminum matrix composite, like economical, lightweight, it is corrosion resistance, machinability and non-magnetic properties. The most wide application of aluminum matrix in aerospace, automotive and marine industries. Then when we look into the intermetallic composite, the reinforcement materials formed from the intermetallic phase in the aluminum itself. So we can get excellent bonding in this kind of intermetallic composites. Some of the example of intermetallic composites are Al3Ti, Al3Zr, Al2Cu, etc. But it is significantly very efficient, but we have to consider the shape, size and weight of reinforcement. In this presentation, we are more focusing on secondary processing technique. The processing it may be processed by two or more processing. That is, we are just say like a single processing or multiple processing, which carried out in the material after the manufacturing immediately or through some other techniques. The secondary processing refine the property of metal in vast manner. Some of the secondary processing technique, including rolling, extrusion, forging, and equal channel angle processing, were used to tempt the desirable microstructure changes. Because microstructure changes is very important while we are considering the mechanical property or to enhance the mechanical property of a particular material. But in case of tensile behavior of intermetallic particles, the changes must need to improve the tensile behavior. But it is difficult to alter the entire microstructure in the initial stage. The plasticite material flow in the above secondary processing techniques are very low while compared to the friction stir processing. The friction stir processing, most of the cases we are used to make a different composite by taking grooves in the base material. According to the volume fraction, it may be differ. It is classified from the friction stir processing. It is nothing but a joining of dissimilar materials. But in this case, we have to consider some of the important parameters like tool, then different parameters like speed, then transfer speed, then depth of plunge, then time, dwell time, etc. We have to consider. There is a lot of research opportunity in this area depending on the tool itself. In this case, we have the three major parameters we have to consider while designing the tool. Number one is shoulder diameter, then tool pin profile, then material of the tool. These are the three important factors. Then what kind of matrix we are going to process. These are the major consideration while we are selecting this process. Compared to other techniques, the other techniques like rolling, forging, equal angle channel press, extrusion, like that, FSP have the following advantages. The first thing is it is a solid state process. Then the process parameter and tool design improve the results. The length of the tool pin can be modified according to the required depth of the stir zone. The FSP component does not undergoes any changes. There is no change of shape and size of the metal after FSP. Then poisonous gases, noise, radiations, totally we can avoid with the help of this type of process. The loss of alloying element was limited. It is very important consideration while we are going for some other process, some losses will be there, but we can limit the losses by this process. Then easy to automate the entire process. There is no need of a specialized machine for that, even though vertical milling machine is more than sufficient for some kind of materials, but it is not suitable for bronze like heavy materials. So for while we are considering magnesium, aluminum, steel, we can go for that. Then the tool is non-consumable tool, but even though it will wear out whenever the process is repeating, we can improve the structure of the material like fine grainment, then defect-free process zone, then rank hole and groove method used for fabricating composite. It is very important thing, that is rank hole and groove method is used for fabricating composites. In this method, simply we can take a groove in the matrix and we will fill the reinforced material, and with the help of this tool we can easily manufacture a different composite with the help of this. So we no need to go for casting or some other process. So it is very compactable and easily we can do a lot of experiment through this. Then in situ reaction takes place during the process itself. because during the friction stir processing, the shoulder will act as a forging component. Then the tool pin will plasticize the material due to the friction heat. The heat will react with the material and reinforcement and will start the incentive reaction during the process itself. Then why we are going for intermetallic composite? What is the reason for that? Lot of ceramic particles are there. Ceramic particle, if we choose the ceramic particles as a reinforcement, the main thing is wettability of the ceramic particles inside the molten aluminum metal. It is very important consideration. While the wettability is improved, automatically we can get more bonding strength. But in case of ceramic particles, the temperature difference between the matrix and particles is highly differ. So we have to consider the thing first one. Then suppose we are going for nano ceramic particles. Again, the molten metal have to weight more area of the nano ceramic particles. It will leads to multifold increases in surface area. So it is not probably we can get a good microstructure or crystal orientation with the help of this. So again, we have to go for some other processes, secondary processing. Then ductility and toughness of aluminum matrix are depleted severely due to the brittle ceramic particles. The ceramic particles will act as a reinforcement. It will lead to the loss of ductility and toughness of the matrix. Then the wide gap in thermal property of aluminum matrix and ceramic particles produce unnecessary microstructure feature during the solidification of the composite. So due to thermal difference during the solidification, the particle will solidify perpendicularly to the matrix composite. So these are some of the drawback of ceramic particles will act as a reinforcement. Then aluminum based intermetallic particles. Mostly the intermetallic particles, tri-aluminum and dialuminate, can be used as a reinforcement phase for aluminum matrix composite. It is competition to the ceramic particles. Even though we are using intermetallic, the intermetallic will produce somewhat equal strengths to the ceramic particle and some of the group of intermetallic particles. The surface energy of those, that is tri and dialuminate particles, is high enough to install wetted by the molten aluminum. Then the physical and thermal property do not deviate largely to that of aluminum alloy. So we can get the actual property of the matrix without more deviation while we are going for intermetallic. Then maintain excellent thermodynamic equilibrium condition with molten aluminum during the casting with result in good interfacial bonding. And the interfacial bonding, it is very important while we are considering the tensile load. So AMCs were produced by considering various method and the microstructure aspect and the other property. But even though successful production and dispersion of intermetallic particles in the aluminum matrix and microstructure was characterized by undesirable features such as pores, segregation, and particle and grain boundaries, particle clustering, particles of coral irregular shape. We simply call as flaws, different types of flaws during the casting process. Intermetallic particles were beneficial to improve hardness and wear property. Most of the research in intermetallic particles have conducted to improve the hardness and wear property. While here we are considering the tensile behavior of the intermetallic composite. This is the basic thing. Whenever we are go for a mechanical side, the grain refinement is one of the important consideration for the evaluation or enhancement of a property of the particular material. While we are considering the grain size, we are considering in three scales. That is from 1 to 10 micrometer. That from 0.1 to 1 and below 0.1. The process parameter can directly affect the microstructure of material and its grain size. It is very essential. What is the parameter? What are the process parameter we are selecting? It definitely affect the grain size of the particular component. Then different processing parameters have different effect on microstructure of the material, which contributes to various mechanical property. Here, whenever we are looking for the enhancement of grain refinement, here this is the basic consideration. The grain boundary evaluation. The grain boundary evaluation is to be observed, then texture of the matrix, then phase transformation. A lot of transformations will happen during the process, so we have to observe the phase transformation and dislocation of particles. While we are adding reinforcement, the quantity must be controlled or it must be fixed, or otherwise dislocation will happen. Then average grain size. If the grain size is high, it will automatically affect the mechanical property. So again, we have to go for grain size evaluation. Here we are considering that grain size evaluation through secondary processing technique. Okay, these are some of the secondary processing technique. In that, intermetallic components in aluminum, how it is forming, that is due to thermodynamic and atomic interaction, particularly during the cooling, solid state reaction or heat treatment. This plays a major role to determine the mechanical and thermal property of aluminum alloys. It is very important thing. Then mechanical property, if the compound is high, it will reduce the ductility, thermal and corrosion resistance. It enhances the resistance to heat and corrosion in aluminum alloys. Intermetallic components will enhance the resistance to heat and corrosion. Then main challenges, the excessive or uncontrolled intermetallic formation can lead to poor mechanical property, that is brittleness or poor machinability. So it is an important challenge why we are considering the intermetallic formation inside the molten alloy or molten metal. It is very essential to consider the quantity of reinforcement to be added in the molten metal and uh, time we are providing to synthesize the intermetallic composite. Then structure. During the process, while we are considering aluminum, suppose I am adding a ferrous iron as a reinforcement for the aluminum matrix. Here, the intermetallic components will attain some spaces in the structure. In Al3Fe, aluminum will occupy 15 parts and ferrous will occupy 4 parts. So the pattern is totally arranged differently. The aluminum atom often form complex framework in the intermetallic, while iron atoms occupy position that stabilize the structure. So intermetallic composite, whenever the intermetallic formation takes place, most of the cases it will start to stabilize the structure of the particular atom. Then while considering the atomic radius and bonding preference between aluminum and ferrous, it leads to the formation of stable crystal lattice. So we can get a stable lattice. Then formation, solidification during casting, thermal treatment, solid state reaction. These are the formation condition for the intermetallic components. Then crystallographic orientation, order structure. Unlike solid solution, intermetallic composite exhibit long range atomic order. That is, the atom specifically occupy the crystal lattice and form well defined stoichiometric components like Al3Fe, Al6M or Al2Cu. One more thing, the intermetallic structure is very complicated and combined for different atomic size and bonding preference. So the intermetallic composite will provide more advantages for the matrix while the formation will take place, but even though it will lead to some difference in the grain formation. So to overcome this, we have to go for secondary processing technique. The main thing is, suppose we are considering rolling as a secondary processing. Here we can see the
Balakrishnan sir.
crystal.
Sir, sorry for the
Sir,
interruption, sir. Sir, PPT
சொல்லுங்க
share.
சார். PPT ஷேர் ஆகலைங்களா?
sir. Screen share. Screen share.
More emphasis.
Yes, sir.
Sir, இப்போ பாருங்க.
Yes, sir. Now chat, sir.
Okay, sir.
Now chat. Okay, sir. You can
Okay.
continue. Sir.
Okay. These are some of the slides you may miss, I think. Okay, while we are considering the rolling process, it is one of the secondary processing. In this process, we can observe that the three EBSD images are there, that the grain orientation is totally different because in this process, the compressive force will act as a refining area. That is the forging force due to the rolling direction and thickness of the composite, it will differ. At the same time, when we compare to the normal direction plane and transverse direction plane, the crystal orientation is totally different because there is no three-dimensional flow of material. During the rolling process, the three-dimensional flow of material is totally absent. That's why the microstructure is looking like this. That is EBSD is looking like this. Here another example, hot rolled 2A14 aluminum alloy. In this case also we can see that that is normal to the direction, then it to the direction, then transverse direction. Here we can observe that the particles are agglomerated. It was not evenly distributed, the rolling process. While we go for extrusion process, it is a sample area of extruded parts. Here we can see the plane normal to the direction, transverse direction and extruded direction. Here the cut section of the portions. Here we can observe that the formation of grain is very fine in the top area. In middle it is totally different. The side also, that is the plan 001 is perfect, that plan 11111 is not perfect. Similarly 101. Here we can observe that the enhancement was happen on the surface itself. But even though we are go for EBSD up to 0.34 micron, it can be easily to observe that. But this kind of changes will not support to enhance the strength of the material. But we can get the grain refinement on the surface area. One more example of extruded component, that is extruded ABSD of the component. Here we can observe that the magnesium was compressed through extrusion process. Here we can see the particle agglomerations. Here also we can see that, but the size of the grain is totally different because due to that compressive force, the force is not evenly distributed. It only distribute on the top area. Then equal angle channel press, we can go for, suppose we are considering secondary process, we can repeat the same process for n number of times. Here we can observe that 1 pass to 12 pass. Here in 1 pass, the grain structure formation is totally different. After 12 pass, it was somewhat refined. But in this case, we can observe that 8 pass have fine refinement compared to other thing. So in this case, the 8-pass equal angle channel process will provide better result compared to the 12-pass. Then forged component, here we can easily observe that while forging what will happen in the grain size and orientations and dislocations of particles. This is also one of the example. Here we can see that according to the direction, that is transverse plane, that is longitudinal plane, the grain orientation is totally different and the size of the grain also compared to A2, B2 is very fine. So we can attain maximum property in B2. Then primary method for grain refinement. Whenever we are looking for secondary processing, these are the primary stage to make fine refinement in the property of material. These are the some of the process. Whenever we select the process parameter perfectly in the initial stage, we can attain through the primary methods itself. Some of the methods like solidification control, thermomechanical process, several plastic deformation, phase transformation, mechanical alloying, then friction stir process, ultrasonic, that is from heat, vibration and laser. We can improve the grain refinement. If it is not possible, again we have to go for secondary process. Then most of the literature will define that whenever we are going for a secondary processing or when we are considering ceramic particles, it is very complicated to enhance the mechanical property while we are considering the tensile load. When we are considering ceramic particles as a reinforcement, it will definitely provide less tensile strength compared to some other method. Then research gap in this area, it is very important for research scholars. That is low wettability of ceramic particles will leads to brittle property of the material. Then however, no evidence on the aluminum matrix found with intermetallic. Whenever we are going for ceramic particles, the totally intermetallic formation is absent. So we have to go for intermetallic to improve the mechanical property. Very few work report based on the in-situ methodology of the composite development. In the minimum and maximum content of reinforcement were not discussed. Whenever we are looking for literature, whenever we are going to start a research, it is a very important thing. What is the minimum and maximum content of reinforcement to be added in the matrix? Most of the cases they will provide us a weight percentage or volume fraction like that, but even though they never mention that if the particular reinforcement exceed or particular reach the maximum value, this is the maximum value and this is the minimum value. Most of the papers they are mentioning that 5, 10, 15, 20 like that, but there is no maximum content of reinforcement was discussed. Then intermetallic particles were beneficial to improve the hardness wear property. Then improvement in tensile behavior was not realized. So whenever lot of researchers researched in the intermetallics area, but even though the improvement in tensile behavior was not realized, a few papers are mentioning that the improvement of so-and-so intermetallic particles in so-so parameter have improved the tensile strength of the particular material. So the property enhancement by applying secondary process also found minimum. The maximum papers they are providing that these are the secondary process, these are the secondary process, but the enhancement parameter, how the particular product was enhanced, the property was very limited. So it has to be find out. Then literature on application of FSP to bulk cast intermetallic AMC is new method, because most of the cases we are getting a sample of 100 to 200 mm length and 10 mm thickness and we will do the research work, but bulk casting method was totally absent. According to my opinion, two or three papers were reported about the bulk FSP because it is very important to enhance the property. Then one more important consideration while calculating the material, what are the quantity of reinforcement we have to add when we are going for research in my aspects. I look into four different materials and calculated the reinforcement quantity also. I will show that. It was in Yeah, these are the important parameters. While in my presentation, I am going to discuss about the four different intermetallics, that is aluminum with zirconium, aluminum with nickel, aluminum with ferrous, and aluminum with copper. Initially, we have to know the atomic weight of the components, that is usually, then molar weight of the intermetallics, then what kind of reaction is going to take place. While aluminum with nickel form Al3Ni, aluminum with ferrous form Al3Fe. Here that is important consideration, casting calculation. Here we have to consider, suppose I am going to cast a reinforcement for 1 kg, that is 1000 gram. What will be the reinforcement weight have to be added? Suppose we are considering ferrous, the die capacity is 1000 gram. The reinforcement I am going to add is 53 gram. Then in that 23 grams going to react and 25 going to last. We have to calculate this with the help of this chemical property, that is atomic weight and molar weight. In this calculation, suppose we are considering 53 grams. Here we can see that total value into gram divided by how much gram we are going to add as a reinforcement divided by 100 minus 812, that is weight percentage 5. Here loss of aluminum, that is the atomic weight is 26.93. Here we can see that 26.93 into here 58.7 in molar weight, that is 136.79. So we have to consider these parameters before calculating the reinforcement quantity in the matrix. This is very important thing. Suppose I'm changing the die capacity is 2 kg, that is 200 grams. Automatically the reinforcement calculations change. So actual volume percentage we can get. Suppose we are considering for 15 weight percentage. So I have to add 353 gram of ferrous. So this calculation is calculated with the help of literatures and some other reference material. It is very essential thing for a researcher to know what quantity of reinforcements to be added while we are going for an experiment. Here we can see the methodology. Initially AA60T6 was used as a reinforcement here. Then in optical image we can see the presence of magnesium and silicon. It is important alloy of this element, this aluminum alloy, that is magnesium and silicon. So in this case the presence is confirmed. The next, these are the different particles added to form the intermetallic composites inside the molten material. So zirconium 70 micrometer, nickel, ferrous and copper were added for the reaction. Then initially the FSME of received powder, that is ferrous, zirconium, nickel and copper. It is very essential to observe the microstructure after the processing. So whether the particles are present and what is the shape and size of the particle and whether the particle size is refined or not, we have to compare with this. Then again, for the intermetallic reaction, how much temperature we have to maintain and for what time we have to maintain. It is actually in this process 850 degrees centigrade is maintained for 40 minutes to ensure the proper dissemination of material. Then quantity of reinforcement as per the calculation I have shown in the Excel sheet, that is 5, 10 and 15%. Then casting specimen below 5%. Witness the agglomeration of MgSi particle, that is when I added 1 or 2 gram 8% of ferrous or zirconium with the molten material, the agglomeration of magnesium and silicon particles will happen. That's why I limited the minimum as 5-8%. The segregation diminished the mechanical property also. Then, if in case the reinforcement weight percentage exceed 15 percentage, what will happen? Automatically, it will reduce the fluidity of molten material. Automatically, during the casting process, the threshold value and solidification will affect. Due to that, the microstructure changes will not happen. That's why I limited that for 15 percentage. The minimum value is 5, the maximum is 15. Here, the reactions and metal powder added in grams. Then fabricated composite, then tool used for this process. Actually, for this process, hexagonal pin profile tool was used with a shoulder diameter of 18 mm. Here we can calculate the parameters like transfer speed, RPM, etc. with the help of design software, design experiment software. But even though the process was carried out on the casted composite plate, so I go for a trial and error method. In that method, 1000 rpm 50 mm per minute and 800 rpm 60 mm per minute and 1200 rpm and 50 mm per minute were used for friction state processing to conduct the trial run. In that, I finalized that 1200 rpm 50 mm transfer speed and tool angle 0 shoulder diameter, it is more suitable for processing the casted intermetallic composite. Then tensile sample preparation. Even though most of the cases we are preparing tensile sample as per the standard, but in this case we prepared mini tensile sample from the friction state processed area. Then optical microscope. In this, most of the researchers doing this mistake. Actually, whenever they are preparing the sample, they are just preparing without any mount. Nowadays, most of the cases we are using mount. The mount is very useful to hold the component in a parallel way to get a more clear surface. And killer reagent was used to as a etchant for this. Then one more thing, whenever we are going for FSME, most of the research colleges they take their sample in the mount itself. No need to take like that. We have to break the mount to break the sample from the mount. So we can easily accommodate more than 10 to 12 samples in the FSME machine. So we can reduce the cost of taking the FSME also. Then optical, we know very well about that. Scanned electron microscopy and optical microscope. Backscatter diffraction, EBSD. Then first composite, that is Al3Fe. While after the casting process, we have to confirm the formation of Al3Fe intermetallics in the matrix. So the XRD is one of the method to examine that. In this case, we are considering figure A 0%, that is which is nothing but a matrix, aluminum matrix. Then 15 weight percentage of Al3Fe added. We can see that the formation of intermetallic peaks, that is Al3Fe at 202 and Al3Fe 400 and Al3Fe at 620 without any other components like Al13Fe4, Al12Fe2 like that. So in this consideration, we will confirm that the quantity of reinforcement added in the molten material and the withstand temperature and time provided for the formation of intermetallic composite is more than sufficient to form the intermetallic. Here, optical image of casted composite. The first one is matrix. Here the peak of aluminum as well as Al3Fe particles are detected in the XRD pattern itself. So it is confirming that the formation of particles is there. During the examination of microstructure, the unreinforcement cast matrix alloy display features of dendritic microstructure. Here we can see the dendritic microstructure. This microstructure consists of several long dendritic arms. This dendritic microstructure results in acceleration of cooling through solidification. While cooling, whenever we are pouring the material, during the acceleration cooling, the formation was happen. Then coral precipitate phase of matrix alloy 60, so that is matrix alloy, and Mg and Fe occupied the dendritic space. In this space, the dendritic area is completely occupied by magnesium and silicon. It is a major alloying element of the matrix. That's why it occupied. Then the phase formation due to the combination of magnesium and silicon are the major alloying element of this one. So it will soluble in room temperature. The dendritic structure will more compared to the B. Then again, next image, fine dendritic microstructure we can see here. I think here the dendritic structure is completely absent. As the content of Al3Fe particle increased beyond 5 weight percentage, because as per as I already discussed that the minimum quantity is 5, because if we go for 4, 3, 2, the magnesium compound, the dendritic structure will form due to the presence of magnesium and silicon. That's why we are going for 5. So the particle manifests. In this case, the most of the particles are in irregular shape and polygon and square morphology. In other words, we can say the aspect ratio of the particles decreases as the weight fraction is increased, like that. Again, the nucleation rate increases as the weight fraction is increased. The increases in nucleation might have restrict the growth of the crystal here. So the intermetallic particles will restrict the growth of nucleus while the casting was settled down. Then here we can see the sharp corners and needle formation of the structure. So it will definitely affect the tensile property of the casted intermetallic composite. The next one, it is a optical micrograph after FSP in the matrix, then 5 weight percentage, 10 and 15 weight percentage. Here we can observe that it is finely refined. Here we can some agglomeration of particles. This is due to the more number of intermetallic particles will totally demolish the formation of dendritic structure. So in this image we can observe that the complete refinement of cast composite was happened. In figure D compared to figure A, figure D was completely refined. Then EBSP map for 0, 5 and 10, 15 weight percentage of casted and FSPED alloy. In this case we can see the grain structure is very high compared to the intermetallic composite, that is 5 weight percentage grain size is comparatively low to the matrix. Similarly for 15%, even though the agglomeration of particles and dispersion of particles is there, the sharp particles morphology and pores are not desirable for the enhancement of tensile strength, we know. So the microstructure to be request to redefine using some other deforming techniques. Here we have friction stir process will act as a deforming technique. The process was used to deform the crystal structure. Here after friction stir process we can observe that the fine refinement of the grain. So in this we can observe that at 15 weight percentage the grain refinement was happen highly. So with this we will confirm that definitely the tensile strength of the particular material is going to improve. Then misorientation angle distribution. The angle distribution during the casting and after FSP. Here we can see that the angle distribution is totally very low compared to the casted matrix. Here, transmission electron microscope image of cast composite. Here we can see the particles and dislocation density of the particular particles. The dislocations are not suitable for the enhancement of strength. Therefore, after friction stir processing, the composite particles and dislocation density was improved highly. Here we can see that the same 500 nanomicron. Then similarly here after FSP. So the particles was completely distributed and it was finally reformed. The sharp corners are totally avoided in this thing. Then similarly, number of higher angle boundaries also absent in this process. Then fracture morphology of cast composite. This one is for a matrix. Then this one after friction stir processing. Then cast 15% of Al3FT and friction stir process. The cast matrix, so it is we can easily observe that there is no fine refinement in this one. After friction stir process, refinement is somewhat high, but even though the fracture morphology is not up to the mark to enhance the strength, here we can see that agglomerated particles and intermetallic particles are finely reformed here, this area. So it will definitely enhance the tensile property of the particular material. In ZR also similar consideration, but as per the consideration, we are using 70 micrometer size of particles. So the particle size is high. This one is casted structure. Then this one is after FSP. So here we can see that the particles are finely refined along the grain boundaries. The grain boundary is also refined very well after friction stir processing. Here compared to Al3Fe, Al3ZR refinement is high, but even though the particle agglomerations was in two different sites, it was not evenly distributed. So comparatively, by observing this, we can easily easily identify whether it is going to improve the tensile strength or not. Then misorientation angle distribution compared to Fe, it is somewhat lower because the particles are finely refined with the by the tool rotation, that is three-dimensional flow of material. At the same time, the forging pressure will act to refine the particles. At the same time, the material will not come out of the shoulder diameter of the tool. So the refinement will happen very fine compared to other secondary processes. Then TEM micrograph. Here we can observe that the particle is very sharp. So we have to break this particle into fine to get more strength. Here the sharp particles in the casted composite was completely overcome by the friction stir processing. While during the processing, the plastic formation and solidification process, plasticity of material and tool stirring force will completely reshape the particle size. Here during the tensile test, we can observe some pores in the Al3 ZR particles. This is due to the sudden solidification and the entrapment of gases and displacement of particles. That's why it was happened. After friction stir processing, it was completely removed. Then Al3Ni at 5, 10 and 15 weight percentage. Till 5% there is no formation of Al3Na intermetallic. After 5 we will observe some peaks in this one. After 10 we can observe more. After 15% of 15 weight percentage we can observe more number of Al3Na intermetallic composite peaks. Then optical micrograph of casted composite Al3Ni. Here we can see the particles are dispersed, but it was not finally refined. After friction state processing, it was finally refined. The path of particles we can observe here. In figure D, we can observe that the fine refinement of the particles.
Balakrishnan, sir.
Sir,
Sorry for the interruption.
சொல்லுங்க சார்.
Sir, actually 6:30 to 7:30 அவங்களுக்கு டெஸ்ட் இருக்கு participants.
சொல்லுங்க சார்.
So shall we wind up, sir? Or
Okay,
if
sir.
any need, we will continue after 7:30, sir.
Okay, sir. Okay.
Okay, sir. So participants, you can complete your test in your Atal portal. After that, all of you must attend the session after 7:30 validity and feedback session. So thank you. So thank you so much, sir. Sir, can we connect in after 7:30, sir, or wind up to itself, sir?
Okay, sir. According to timing, we can manage, sir.
Okay, sir.
Yeah.
Okay, sir.
Okay. Okay.
Okay, sir. Thank you, sir.
Thank you, sir.